And yes, it's 3:05, so I think it's good time to start. So we can start with the presentation, Yannick, if you could share that on the screen. Perfect. So now I move to the agenda. So I'll do a little introduction for everyone, especially the people that don't know a space innovation or IGLUNA, just that everyone's aligned. And then, of course, our highlight is for the students to do their pitches. So they have two slides per student, so it's like 2 minutes per team, presenting what's their project, their objectives, and also their results and their next steps. And then we have this Q&A session, and then I'll just close at the end to conclude the event. So as we start, I would just like to present what is space innovation. So space innovation is a unit at EPFL in Lausanne, also at ETH in Zurich. And it's a national kind of center where we want to strengthen Switzerland's space capabilities, not only in Switzerland, but also connecting abroad all around the world. We want to enable space technologies to contribute to sustainable development, and we have already a solid national and international recognitions with access to the cutting-edge technologies being developed for space. And we have members all around Switzerland, and one of our mission objectives is to help our members with their goals. Just to show you here our maps of members in Switzerland, we have different research organizations, universities, and industry doing space-related activities, and we support them. So that's one of our activities, and another of our main activities has been IGLUNA. It's this ESA Lab project where we want to engage students actually not only across Europe, we also have Canada as part of ESA member states to showcase innovative technologies. So the topic of the 3 IGLUNA editions we had so far is to demonstrate how to sustain life in an extreme environment. So this is, of course, useful for space, like on the moon has been the main topic because it's the next step on the space roadmaps. But also this extreme environment, it also helps to develop technologies to improve life on Earth. And with this program, we also aim to educate the next generation of space experts. So it's the university students at the moment, which will then go to work to space agencies, to industries, or say in academia. So to teach them about how space projects works and also give them opportunities to continue with their career in space. And it's also very interdisciplinary, this project IGLUNA, because it has a habitat. So there's architects, there's designers, there's a lot of engineering, there's science going on, as well as life support systems of biology, agronomy, and design projects coming out of this. And it's a bottom-up approach, so it's students proposing their idea, and we help them develop it throughout a one-year program for each IGLUNA edition, and we also try to push the technology transfer, so from the academic research to a commercial application. And so far in these 3 IGLUNA editions, we had over 540 students joining, coming from more than 20 universities across the world. So I'm changing to the next slide, and here it is. What's IGLUNA in a nutshell? It's a platform for students, as I said, to develop their technologies and to increase their readiness level while they're learning about space project management, because we want to boost space exploration. So we really believe we need these type of platforms to create innovative ideas that will land one day on the moon. And how we do it, we build the collaborations with the industries as well. We connect students coming from the universities to industries, research organizations, and other space agencies. So we have an expert board that helps students throughout this academic year, giving them inputs about their projects and helping them for their reviews in order that they successfully reach their objectives at the end of the field campaign. So students are working throughout the year in their university, in their country. They're supervised by a professor usually. And then they come to Switzerland for different events, like we have a kickoff event, a midterm event, and a field campaign. So now someone changed the slide for me, thank you. And this is how it goes, the year program running from September to July. And we have the different events, like I mentioned, and we also have the different reviews, like preliminary design review, critical design review, and readiness review. These are the reviews used for systems engineering best practices, so how space projects run. And we also with these teach students about requirements, interfaces, and everything that is needed for space projects, of course, at the student level in a project of 1 year, so what's visible in there. And the main goal is to come to the field campaign to test their technologies. So in the next slide, now I clicked on that. Yes, we have the field campaign. this is what happened this year in IGLUNA 2021. So we were in Lucerne now in July for 9 days, actually a bit more, first for preparation and then afterwards for disassembly. And what we prepared was this test bed in Mount Pilatus on the top and also at the lower gondola station in Krinserek, where students placed their technologies there. And the challenge was for them to control and monitor from the downtown at the Verkehrshaus, the Swiss Museum of Transport, where we prepared an exhibition and a control room. So these lasted 9 days where students set up their technologies, managed to do some tests, and now they will share the results with you. And just to give you a glimpse of what happened, because it was a hybrid event, so of course we're still living in Corona times. You see everyone there with the mask. Some teams managed to come to Lucerne, but some teams unfortunately could not make it and stayed home. But it was still a hybrid event, so everyone joined. And you can see here we were recording. Everything is available in our YouTube channel. We have live streams from the inauguration, the closing ceremonies, and different presentations, as well as the project shows where every student team presented their project. Here you can see the Museum of Transport. That's part of the exhibition. In the lower corner, you can also see there's Yannick in the control room. So the control room had the different screens and the computers, so students could work from there and control their experiments that were in Pilatus. And here is how it looked like on top of Pilatus. There was a tent protecting some projects there, like the greenhouse you see, and some projects also outside, like the Rovers. And now you will learn more about each of the different projects in just a minute. Here we had some special guests joining. Maybe you can recognize Thomas Reiter. He's just in the middle of the group picture. So he came to visit the students, did also public presentations, which was very inspiring. And we also had other guests from ESA joining us, also from the Swiss Space Office, and our experts from industry, from research organizations and other universities as well came to visit us. Some joined in person, some joined online. And of course, it was open to the public and to media. So it was quite an exciting event, this field campaign, just happening a few months ago. So now I will give the word to the students, and we'll start with project 1, who will tell you more about their projects.
So I'm Kepler with PO1 Growbot Hub, and essentially our contribution to the Lunar project is a system that is capable of autonomously growing plants in a closed-loop fashion so that the astronauts may eat them. So by autonomously, we mean that the astronauts should not have to interact at all with the system for it to be producing plants continuously in the background. And closed loop, meaning that once the system has been completely set up on the moon, it should not require any more resources to be brought from Earth to be able to continue to function normally. So why is this interesting? Well, efficiently growing food is very much a challenge on Earth and in space. So for instance, the aeroponics module that we're developing could be used for instance, urban gardening or urban farming, but also because we're developing some computer monitoring technology for the plants, that could be used for several kinds of plants on Earth and perhaps even crops in the future. How are we doing this? So we have some very creative and very skilled EPFL students who are helping us. And but really the crux of our technology is aeroponics. And what we're trying to bring to it is some kind of innovative software and innovative robotics to make sure that it's entirely closed loop. So for the field campaign was actually one of the first times that we managed to build our robot and bring it online because of several delays during the year. And as many things do the first time you build them, this one had technical issues and engineering issues. So we spent a lot of time during the field campaign overcoming them and addressing them. But we managed to test some things on the side. And for instance, we were able to control the system remotely, which was one of the requirements from IGLUNA. But also we realized that our aeroponic system was capable of growing and sustaining the plants for the duration of the experiment, which is a very encouraging result. So now we are back in Lausanne. We are still working on the robot. We're still very much motivated and optimistic. And we have this prototype, but we don't feel like it's quite there yet. So our goal this year is definitely to keep working on it and making sure that this design can reach its maximum potential. Thank you.
Hello, everyone, and welcome. I'm Riccardo Estivalessi, and I represent LoopSem. Can you hear me? Okay, perfect. I represent LoopSem, a group of basically 20 people coming mainly from Sapienza University of Rome, who dedicated this year to move towards a single goal, which is exactly what LoopSem stands for. LoopSem, in fact, stands for Lunar Operative Outpost for the production and storage of microgrids. We know that on the moon, we cannot overly rely on supplies from Earth, and therefore we decided to find an efficient way to provide humans with both protection and fresh food in situ, thanks to our lunar greenhouse. This year, in fact, we worked on some main features of this lunar greenhouse, basically a micrometeorite shield, an automated cultivation system, and a bioconversion unit. Basically, all of these were represented also in a VR environment. During the field campaign, we managed to showcase the micrometeorite shield in the museum, although we weren't able to participate there physically. Instead, in Italy, we managed to run a full cultivation cycle, and this was thanks to our automated cultivation system. We also had the project show that is now live on that is now on the Space Innovation YouTube channel, and there you can see a deeper insight of each section of this project, and basically also the VR that wasn't really present live in the museum. For the future, we're planning on presenting our work in Dubai at the International Astronautical Congress of 2021. And we are going to expand these studies on the materials for the shield, but we are also going to still keep working on the cultivation system, moving towards the goal that was designed this year and was represented in VR. Thank you for your attention.
Okay, hello. My name is Adrian Ricardes, and I am part of the. Well, it's not saying my. Wait 1 second. Yeah, it's seen now. Yeah, okay, it's the same. So we actually focused on this project that is lunar ice extraction and electrolysis. This is a Lite rover, in this case, a remotely operated from the control room robot that was on Krinserek and also in Pilatus Kuhn. So the what is to extract water ice in order to perform an electrolysis process by moving this semi-autonomous rover. Why semi-autonomous? Because we are searching for a cooperation, a collaboration between machine and human. So this could be scaled for the why in this case. In situ resource utilization is really important in the future because we search for a moon village. Also, the water ice it's a really hard resource to get from the moon in this case. And we search also for the semi-autonomous operation of robots, not only on the moon, but also here on Earth, for solutions for the society. And also we are exploring methods for solar energy utilization. And how is doing this independent, making these independent modular systems for experiments, and then we could unify everything, provide some local test results, and finally remotely control this semi-autonomous rover on the IGLUNA field campaign 2021. Yeah. So we are students from the TU Berlin. How can I change it? Yeah, thank you very much. So we have actually 4 images here. We were a 6-student team. And you can see here also how the control, the remote control was successful. And the results are based on a successful remote control. The exhibition was one of the success criteria. Payload demonstration, in this case, 100 grams of ice in 30 minutes, and we collected 60 milliliters of water. And by performing the electrolysis demonstration, you have here in 20 minutes how to separate this hydrogen. And the outlook basically is to scale this for their missions, and we are searching for more collaborations with other universities and institutes. Thank you very much.
Hi, my name is Gabby, and I'm from the Sample 2 team. This year we presented a project consisting of Terraform Lunar Soil that we use bacteria to perform the process. And we did the process in order to reduce the resources brought from Earth and to make a sustainable growing sustainable growing modules on Loon. And our main goal this year was to plant the seeds on the soil, and we did that in the autonomous module. You can see on the photo on the bottom right. The seeds have sprouted, so the overall the idea is there, and the part of the sprouts were successful, but we still are performing some more tests on the soil. Fortunately, all the biotechnological experiments take time, so we're still waiting for the actual results. But we're very hopeful and that the project looks very promising. Yeah. And the module, the autonomous module that we presented during the field campaign worked flawlessly during the whole duration of the campaign. And we were very happy with the results we got in there because the right environment was sustained during the whole field campaign. Thank you.
Hello, everyone. My name is Juan Carlos. I used to be the team leader of X2 Space, the project team with a technology for the production of glass fibers from locally available resources, in this case, lunar rock. As you may already know, the transport of payloads into space, such as, for example, for research missions or the construction and the supply of manned lunar stations, pose immense economic challenges in addition to technologically complex tasks, with cost for payload transport of 1.1 million euros per kilogram to the lunar surface. But nowadays there is new advancements that may make this price cheaper. But nevertheless, space projects require large freight volumes, and the weight reduction seems to be essential. However, the raw materials from the moon or even Mars in the form of regolith are suitable for producing habitat building materials and thus reducing freight cost for further missions into space. For this purpose, continuous mineral fibers, that is basaltic glass fibers, can be utilized in situ. And to produce fiber composites, as well as thermal insulation, filters, and hydroponic mineral wool for plant cultivation, among other things. However, this requires a spinning machine that can be operated under space conditions. And due to the limited space available within the space elements like a rocket, the system for the spinning technology must be miniaturized. Therefore, the goal of our project was exactly the development and the design and construction of a miniaturized spinning machine for the production of glass fibers under vacuum conditions. So in the next slides, you can see that for the field campaign of the IGLUNA program, our system was tested and served as a proof of concept of this spinning technology, which is part of the Moon Fiber project at RWTH Aachen. Therefore, we were able to validate the correct operation of our system under different environmental conditions as in a laboratory, as well as various parameters of the manufacturing process. We got enough data to refine some of the components. All visitors to sponsors were extremely satisfied, as we had team members who were answering all sort of questions, and we have enough infographics. If that wasn't enough, we had also prototypes of the project, mini satellite. We plan to ship our machine into space, and fibers produced from moon rock, simulant. And of course, we had a successful drawing initiative where children could use their imagination and draw a future use of our fibers in exchange of some candy. We are very grateful to all our sponsors, especially Maxson Group and Laushat GmbH, and of course to everyone that supported throughout the project, especially in the Moon Fiber team. Thank you very much, and Godspeed.
Hello everyone, my name is Lyubov Dimova and I want to present you our project P06, the Inflatable Lunar Habitat. Our idea is to build a technology that is lightweight, flexible, stable and offers space for scientific experiments and can be used in extreme environment on the Earth and one day on the Moon or Mars. The reason why we work on this project is because now more of the scientists are fixed to their location. So being able to independently assemble, disassemble and transport their laboratory, we want to make them more autonomous and in the same time to keep them safe and well equipped for their mission. In order to achieve our goal, we worked on many designs until we created our first prototype, which we in turn tested and will continue to test in different conditions so that we can find its problems and improve it until we get a working habitat to meet all our requirements. Our first big test was on the field campaign in Lucerne. You can see on the picture left how it looked like it. In general, we can say that we are satisfied with the results we achieved during the campaign. However, many problems arose during the testing the prototype of the habitat, which we will solve from now on. But on the first points is finding sponsors so that we can continue with the practical improvement of the prototype. During this time, we will work on cleaning the individual problems with the constructions, but for now only theoretical. Our next big goal after finding sponsors and improvements is to test the prototype in much more extreme place than Lucerne, and in addition to the structure itself, to test it through use by scientists, even for a few hours, so that we can get a direct and specific feedback from its future users. So thank you very much for attention.
Hi everyone, I'm Maximilian. I represent the P07 Collaborative team, which stands for Collaborative Rover and Drone. Our ultimate goal is to enable autonomous exploration mission with robot systems on the Moon and on Mars, and in reducing at maximum the necessity of human in the loop. So we focused our work on navigation algorithms, such as a mapping algorithm, path planning algorithm, and task planner algorithm. During our field campaign, we wanted to demonstrate some capabilities for our rover and our drone. So we used our drone to fly over an environment which was unknown, and we created a map with it. Then we sent the map to the rover for it to use it in order to explore and visit some objectives on the ground. And so everything was successful. We were very happy with our results. The drone flew autonomously. The rover created its action plan autonomously with the task planning. And we also managed to make the rover visit the objective autonomously, even though we had a bit of struggles with the grass on the environment, which created some bugs in the algorithm. So our team is currently working on improving the path planning algorithm of the rover, and we are starting to investigating the human factor related to the control center operations. And that's very it. Thank you very much.
Hello, my name is Panayota Bosco and I will be presenting P8 project Lite today. Let's start with the purpose of Lite project. Lite aims to be a general tool for astronauts' navigation and assistance. Its goal is to facilitate and simplify future exploration missions, either real or analog. And to achieve that, we build a prototype augmented reality system to target astronaut problems. This system was built on the Microsoft HoloLens, which is an AR headset. Due to budget restraints and coronavirus, we could not attend the field campaign in person, but we did attend the virtual field campaign. And here you can see the environment in which we filmed our demo video, which we presented there, and where we also tested our system under more realistic conditions. Thank you very much.
Hey guys, so I'm from Lunar Zebra. I'm Simon. I'm the new chief engineer. And before I start with IGLUNA, maybe we should talk about what Lunar Zebra is in general. So Lunar Zebra is a faculty project from TU Delft in the Netherlands, and we build lunar rovers, which are inexpensive and light, and can be used as a variable rover for any kind of payload, really. And overall, our goal is to put a swarm of rovers actually on the moon. And that's why we're part of IGLUNA as well. So what we actually did in IGLUNA was to design a swarm of self-deploying and inexpensive miniaturized rovers that had the goal of finding predefined targets somewhat as a swarm. So the reason why we're doing that is because swarming technology is not only useful on the moon, but also can be used on Earth, and the rovers for IGLUNA will be used as a demonstration swarm on Earth as well. And how we did that, so as I said, the rovers are supposed to act as a swarm on the moon as well. So in IGLUNA, we were mainly testing the rovers in a more basic version of the swarm, a bit more centralized, and we plan to develop that further from now on. But yes, so what did we do in the field campaign actually? Tatiana, if you could. Thanks. Yeah. So during our field campaign, we tested controlling a rover, from the control room first of all, to see if that works, and that actually did work. So we were able to remote control things on our test bed. And we also demonstrated that we can wirelessly charge our rovers in their docking stations, which can be seen on the right upper picture on your screen. We also demonstrated that the rover can walk on the test bed. However, due to a few failures in the electrical system, we were sadly not able to demonstrate the whole swarm as it should have been. However, we are still working on it, and we will finish it within the next 3 or 4 months, I think. We have found the problems that we had and are now fixing them, so the swarm should be ready soon. Once we have that, we're going to develop a better swarm, one that actually involves inter-rover communication, for which we're still looking for collaborations with other universities to maybe test out their swarming algorithms. But yeah, so on the side of that, we're also still developing our lunar rover, which hopefully will also fly in the coming years. And yes, I think that's pretty much it. Thank you.
Hi, I'm Pierre from Team ESA Lab, Multirobot Explorer from Polytechnique Montreal in Canada. So our goal in IGLUNA was to produce a self-organized team of robots for exploration and mapping of challenging planetary environments. We want to prepare the technologies for future multi-robot exploration and enabling collaborative human-in-the-loop missions, in which a human controller has minimal actions to take to direct the swarm of robots. We deployed our team of robots with sensors, camera, lidars, collecting valuable terrain data, and we also collected the human connection metrics on the human operator. So unfortunately, due to COVID, we couldn't go to Switzerland, but thanks to our awesome partners at the Canadian Space Agency, we could test our system on their Mars analog terrain in Montreal. And you can see some pictures of our tests, and also on the bottom right, some pictures of the resulting map and the VR setup that we have for the human operator. So we managed to demonstrate autonomous exploration and mapping without GPS, enabled by human supervision through VR at 17 kilometers away. And we plan to continue working on this system, and hopefully in the next few months we'll perform a user study to measure the cognitive workload of the operator in such systems. Thanks.
Hello, I'm Saif, and this is P11 Project Rebels. We are part of the scientific work group for rocketry and spaceflight at the Technical University of Munich. And our goal is to show the feasibility of combining solar sintering technology on a rover. The goal of this combination is to enable the automated construction on the moon by in situ resource utilization. Our rover, as demonstrated in the image on the slide, integrates a Fresnel lens on its payload and uses it to concentrate sunlight onto rigolith simulant, thus achieving the temperatures necessary to sinter. Rigolith then hardens up and it can be used as a which.
Oh, I think we lost your connection. Saifullah, are you there? Maybe try switching off the video. See if we can hear you better.
Hello, I think
Yes.
I lost connection.
Yes, now you're back.
Okay, good. Continuing. Yeah, our rover integrates a Fresnel lens on its payload, which concentrates sunlight onto lunar regolith simulant, thus achieving the temperatures necessary for sintering the regolith, i.e. hardening it up, which can then be used as construction material for infrastructure, such as roads or landing zones for rockets, as well as protective shells for inflatable habitat modules. During the IGLUNA field campaign, we tested the driving and the sintering capabilities of our rover. Some of the sintering results are demonstrated on the image as seen. One of the major problems that we had during the field campaign was the absence of sunlight. Due to weather conditions, it was pretty cloudy and it was cloudy at some times, which caused the sunlight focused by our Fresnel lens to be pretty inconsistent, thus messing up the sintering results. However, due to the absence of atmosphere or clouds on the moon, we will not have this problem on the moon. Our systems have shown promising functionality. However, we're not very compliant with our standards for robustness. Should this technology be one day deployed on the moon, then it should comply to a certain standard work. Therefore, our goal for next year is to further develop and perfect our current system, thus ensuring sustainable work environment for future project iterations. Thank you so much for listening. Back to you.
Thank you. So now I will represent Power Hub because their semester has not started, so they're still in a very well-deserved break and they could not join today. But there are a very good team from University of Glasgow in the UK, in Scotland. So what the project is to demonstrate a lunar habitat power generation and storage, and they have different systems for this that they actually they could not come to Lucerne because also of the COVID reasons this summer, but they joined the virtual campaign and they tested their systems at home and they participated with a project show. So why are they doing this? We need the wireless power transmission, the fuel cells, and the nuclear fission for lunar applications. And they did this with physical prototypes and computer simulations so they could showcase their technology. So what they did in the field campaign, in the virtual part, they demonstrated the viability of the hydrogen fuel cell and the wireless power transmission prototypes, and they proved that they were reliable and resilient for the generation of power. They also discussed about solar power satellites because they also have some design for that and their nuclear technologies. And in the project show, they provided novel insights into how power can be generated and stored for a lunar base. So these were all the student teams that we had this year, the 12 student teams with what they did, the results and their next steps. So now it's that time for Q&A session, interactive. Maybe if you have a question, I don't see anything written in the chat, but if someone from the public has, I see some experts have joined, even some journalists. If there is a question for the student teams, please just unmute yourself or write it on the chat. This is the time to interact with the teams.
Hello, here's Nico from Maxson.
Yes.
I think I had a question I was starting to write in the chat, but if nobody has a question, so I can also start talking to you. So I have a question, especially to the I think the P11 rebels, and I'm not sure what the I think both of you are planning to go with a rover, but why you decide to go with a mobile system? Especially you are working with an optical system on the lunar surface. You have to expect micrometeorites, you have to expect dust, and you have to how should I say, to be sure that you will not change your optical parameters, so that your system will be robust against it. So, and this is, I think, why you decide to go with a rover.
So that's P11. Would you like to start,
Yes, of course. Yeah. So, well, the original thought about the rover came from our team. So, for us as a team VAR Exploration at the group at our university, our goal has been since we were founded was the development of rovers for planetary exploration. At a certain point, we came about the idea from some research that the European Space Agency has been doing to work with solar sintering. This is how the combination of rover plus a solar sintering payload came to be. It's sort of has been our team goal always to develop a rover, and because we wanted to do something more scientifically oriented and research oriented, came up about the idea of the solar sintering. I hope that answers your question too.
Yeah, partially. I think the idea with the solar sintering is great, definitely. So, but as I said, I think it is really challenging to go with a rover system. So, also from my point of view, if you go with a fixed system and you build up, for example, a rover who is collecting the dust and bring it to your system, could be more efficient and especially better for your how should I say, for the robustness of your system. Compared to a rover where you have implement all the safety mechanisms to protect your lens against dust and micrometeorites, for example. It is only a point. Also, it is clearly a point of view, and also perhaps you know Maxson. Also, we are building actuators for several rovers systems, and so I know there are a lot of rover developers around the globe. So you will be not the first one, and you will be more or less one of the latest one. And so I think you could it could be more efficient to buy a good developed rover collecting the samples and for you and bring it to your system, for example. So, because you start at the moment from the scratch, also with your rover and your combined system. It's only a thought.
Yeah. Of course, that seems to be a very valid point of view, and it's also something that we had in consideration during the design phase of our system. However, what we want to, as you said, there are a lot of rover manufacturers. Experiments with solar sintering or sintering technologies in general, so that is also not something new that we are developing. So the same argument can be said there. We could also buy, some solar technology and utilize that to. Because we wanted to go an innovative route and try to make something new. And this is actually what we are focusing on mostly, not to build the most robust rover technology or not to have the best solar sintering results, but to interface those two technologies together and have a mobile solar sintering station, let's say, which would have, in our opinion, a lot of benefits should there be a lunar colony established at some future point, because then you are not physically constrained to a certain point. You don't have to transport regolith around as it's available all over the lunar surface. You would have the rover just drive up to it and would center a strip with a certain width, and that is a road. An approach which might get probably more complicated if we have a stationary sintering station which hardens the regolith, and then that would have to be transported back, laid down as a road or something similar. But yes, definitely, I understand your point, and it has been something that we have heard during our design phase. Start from scratch, but in the end of the day, we are also just a student team with a knack for work and wanted to build our own rover, I suppose. So that is.
Yeah. It's clearly something driving is really cool. I understand you fully. It was just a thought.
If I might add something, I think a part of the question was a little bit lost on my colleague here. So I believe you are asking about why exactly we want to move the entire system, correct? Perhaps we didn't communicate that clearly, that we want to print the structure directly, not print some intermediate material like bricks that will then be transported somewhere else. Like, we wanted the flexibility of being able to land on a certain area and then be able to relocate to a more optimal area for habitat construction and print the structure directly on the ground, so that we can be a lot more flexible with the placement. And we have started to think about issues about the scalability of the rover. For instance, a very large rover would be able to print the structure in one go, but then we are also considering concepts where we'd have smaller rovers that would actually drive on the structure itself and just circulate around it as it's going along. So in this regard, that's why we needed to integrate the sintering payload onto a mobile platform.
Okay. I think now it is it's more clear. It is sure some challenging or some challenges to realize such a system. But okay, your point of view is now understood. Okay, thanks.
Perfect. Thank you, Nico. Perhaps also your question was also directed for P3, Louis. So Adrian, also if you want to explain why you chose to do a rover and not just your platform, a static platform.
Yes, for sure. Yeah, it was indeed related with that project. We had actually several options in the beginning. We discussed as a team before stating the mission requirements. What could happen if we could have a fixed structure, for example, in order to collect the light, or in order to materialize, so something inside of a dome, or just a mechanism to redirect the light. So we discussed this several times, and we found that basically it was statistically speaking, we are taking advantage of more and more robots on the moon and also on Mars. So since we don't have too much information right now exactly how to get resources in a way of being really cheap, we have to search for some other alternatives. So we actually found an article that is from the Colorado School of Mines that are actually developing this dome. And we thought, okay, what could happen if we apply this dome in order to demonstrate that a rover, a mobile mechanism, can handle this payload. So this could be not only fixed, but also modular. So the modularity was the main intention of this demonstration. Maybe in a scalability small, but we could scale it up to fixed structures and also to attach this payload to any rover or even to a moon village. So that was one of the main purposes, personal purposes also from the team, why we selected this. And of course it's challenging because we cannot put a 50 kilograms mechanism on a robot. It's really difficult, but it could be miniaturized in the future.
Great, thank you, Adrian. I don't know if Nico, this was good for you, or you want to follow up on something?
It's fine. It's fine for me. It is clearly a point of view. We have different point of view on such a topic. It is interesting too, as the first one. As the rebels, it is clearly understandable why you do this. The point is how you want to it is seen in the entire complexity of such a mission. So if it is really useful to go with such complex system on a mobile platform, or it is go with a fixed system, or perhaps a partially mobile system, it depends what the reality really needs and what challenge you have to solve your problems. So that's the point. As I said, I have a different point of view on this topic, but your decisions are clearly understandable.
Yes, very good inputs. Thank you. Would someone else have a question before we run out of time? I see Grace wrote, all the projects are so great. Well done to all the teams. So congratulations from Grace. I don't know if someone else that joined wants to ask something else. This is your chance. I think no questions. Okay, so I think now we can conclude. So I will go back to the presentation. Yannick, if you can share that again. Perfect. So before we close, I would like to thank once again all our partners and sponsors. I have some light in the middle of my face. There it goes. It's a bit better like that. Yes. Good. Yes, so all the universities that participating this year, all the student teams that you just saw, and where they're coming from all around Europe and Canada as well, and all our different partners, particularly in Lucerne. We were hosted by the Verkehrshaus, the Swiss Museum of Transportation, Also Pilatus, Hochschule Luzern, they also helped us with the remote control setting. Rheintech also did the control room. The Tourismus from Lucerne and also from Switzerland also provided some nice goodies for the participants and for our guests. We also had some discounts from Swiss Youth Hostel and Holiday Inn Express, as well as from India Celt, providing the tent at Pilatus and Textile Point for the t-shirts of IGLUNA. So we would like to thank everyone, also everyone that joined this webinar today. Thank you for joining and listening in. And now just to conclude on the next steps, so of course with IGLUNA, our vision is to take the student projects to the moon. And as you heard, all the students want to reach that goal, hopefully in the near future. So we try to be like a stepping stone in them to prepare, providing this testbed here on Earth to prepare for future lunar missions. And at the moment, we're looking for funding, so we're open for collaboration so we can continue with this IGLUNA activity. So of course, you can always write to us if you want to collaborate with us, if you want to discuss with us how to move forward. Here is our email address and also our website where we have also more information about IGLUNA. We have also the field campaign videos, so those are also very nice to watch to see what happened during this field campaign and also on the previous editions. So I think that's it on our side. We're just on time. If anyone wants to add anything else? Nothing? Thank you, everyone. It was great seeing your results in such a nice way and your next steps. So we wish you all the best. And we hope to stay in touch and to keep collaborating in the future.